So I'd like to welcome you to this meeting on behalf of the organizing and the scientific committees. I'd like to welcome you to the Institute on behalf of IMPA. And as a Carioca, I'd like to welcome you to Rio. You know, a Carioca is not a person who is born in Rio, is a person who makes Rio their home. So I just hope that you feel like a Cariocas here. You feel at home. Okay? So I'd like to thank the scientific committee, Hannah Markvig, Margarida Mello, Matt Baker, and Jose Ignacio, who is here among us. I'd like to thank my colleagues of the organizing committee. It has been a pleasure working with you. Ana Maria Botero is there, and Roberto Gaudi, Eduardo Vital, my ex-student, Marco Pacini. It's been a pleasure. I'd like also to thank the support that we received. We received financial support from several agencies here in Brazil, from IMPA also, but also from CAPES, which is the federal agency, FAPERJ, the state agency, and INCTMAT, which is a virtual institute for science and technology, coordinated by our colleague, Jacob Alice. We also received financial support from Germany, from Bielefeld Universität, and TRR 358, the Collaborative Research Program on Integral Structures and Representation Theory. I don't think you want me to say that in German, I guess. Okay, so let me point out that this is not the first meeting of its kind that was organized by IMPA. We had a first meeting which was on tropical geometry in the tropics in 2015, and then another meeting, tropical geometry and moduli spaces in 2018. They were both organized by Oliver Lorscheid, who is among us. He just entered. Oh, he's there. So he is one of the few people that came to the 3 meetings. I think there are more. Ethan is there. You came to the 3 meetings as well, right? Yeah, I guess so. But right. So, and Kris also. Yes. You came to all 3 meetings, right? So the first one you were in Berlin. Yes, and the last 2 in Oslo, Norway. So Kris came all the way from Oslo, Norway, and I know what you're thinking, but last time she came from the sunny Norwegian summer to our frigid winter. So, okay, let's see what else I have to say. Okay, so maybe I have spoken too much without stating any theorem, so let's start. So Kris Shaw comes from Oslo, Norway, and they agreed to give us a mini course. So the first lecture of today, the mini course is on combinatorial geometry and Hodge theory. So please, Kris.
Thanks, Eduardo, and thanks to all of the other organizers. Eduardo, yes, go. Where should I? This?
To turn on the microphone.
Oh, thanks. Thank you. It's been too long. Okay. Thanks to all the organizers for having us here. And yeah, indeed, it's the 3rd time that I get to be at an event on tropical geometry organized at IMPA, so it's a great pleasure to be here. And I hope that in my 4 lectures, it's also a very generous amount of time, I will tell you about synergies between, well, combinatorics and geometry, in particular Hodge theory. So in order to start, we're going to go one direction from geometry to combinatorics via so-called tropicalizations. And I hope that by the end of my lectures, we'll see that there's interest in trying to go back to try to use geometry or inspiration from geometry to study some combinatorics. So let's start with algebraic geometry. And let's say we have some subvariety of the complex torus. Okay, and we'll define the tropicalization. First, the definition of tropicalization to be, well, some sort of limit of the coordinate-wise logarithm of all of the points in V. Okay, so let's get a feeling of this with an example. So if our V is this line in C star squared, I've drawn it in R star squared, okay? Then this log base T map, first it's going to take, well, the absolute value of each coordinate, then apply logarithm base T, okay, and then take some limit. So let's do it in stages. If we first just take the absolute value of each coordinate, then we get something in the positive reals. Okay, that's just flipping this up to all the coordinates being positive. But we do have complex points, and those will lay in the inside of this strip just by the triangle inequality. Okay, so we actually have this two-dimensional strip once we take the absolute values. And so this map is kind of violent. This absolute values is not a very nice map. But now the logarithm is a nice diffeomorphism. So what we get here is a kind of so-called amoeba of the line. So this is the amoeba in the sense of Gelfand, Kaprenov, and Zelevinsky. And taking the t to infinity is just going to make this kind of spine-like figure, or this amoeba-like figure, retract to its spine. So we get something that is just this tripod graph in the plane. So this will live inside of Rn. Okay? And what we want to know, basically, from our lectures is, well, what information does this picture here know about our original variety? Okay, so the main question is, what does this tropicalization of V know about the original V? And well, one thing it always knows is its dimension. We started with something of complex dimension 1, and we get something of real dimension 1. That's always true. There'll be a sense in which it kind of knows the degrees of the defining of the original variety. So there's a sense in tropical geometry of this being degree 1. But for that, we'll need some geometry in this new world. We need a definition of, say, degree. Okay. The main interest of my lectures will be, when does this picture here know anything about the cohomology of the original variety? And not just cohomology, but let's say Hodge structures or mixed Hodge structures. Okay? There's various other things that have been developed in this geometry that help us to recover information about algebraic varieties. For example, enumerative geometry. Intersection theory is something that I'll also touch on in my lectures. But the kind of issue is always two things. One, developing the geometry here, developing invariants that will kind of transport back. Okay, so knowing what the right definitions are in this kind of under the log world. And the other thing is those definitions won't always work. There'll be kind of a class of varieties that when you tropicalize, you'll get to retain more information than others. Okay? So for example, we could take some other varieties, say that are conics. So V, say, is a zero locus of some A plus X plus Y plus XY. And depending on our parameters here, this could be a singular conic, product of two lines, or it could be a smooth conic. However, the tropicalization is always the same thing. It looks like this kind of union of two lines in R2. Okay? So even though the geometry of the nodal curve here is different from the geometry of the smooth conic, we get the same picture with no other extra information. So there's kind of no way to be able to tell the cohomology of both of those two spaces from this picture because they have different cohomology. So V could be a kind of nodal nodal curve with 2 punctures on each sphere. Or it could be a kind of 4-punctured sphere. Okay? So not possible. The same tropicalization, but different topologies. Okay, so not only are we looking for definitions of, say, cohomology in this realm, but we're also looking for caveats, conditions of when or any recipe for the cohomology from these pictures will actually work. It won't be under all conditions. So today I want to show a bunch of examples of when it actually works for certain varieties, subvarieties of the torus, when their tropicalizations can recover the cohomology and even more information. And from there, we'll try to build on that. Okay, so in order to continue, I want to look at what are the structures of these tropicalizations. Okay, so for some of you who have seen tropical geometry before, you might have a definition in mind of what this, of how to get from a variety to some tropical picture. I think we'll see a different definition in Farbod's lectures as well. We could also use, if we have a variety defined over a valued field, a field with a valuation, which whose image is dense in the reals, we can, instead of taking log of the coordinates and some limits, we could also take image under coordinate-wise valuations. And then there's also a definition of the tropicalization via initial ideals. Okay, so I'm just saying this for those who may have seen this before. These are all the same, up to maybe taking a minus sign in each of the coordinates, because I'm using a sort of max convention and the others use a min convention. But in any case, what is this trop V? It will always be equal to the support of some polyhedral complex. So this is, P is a polyhedral complex of pure dimension, and we'll say that D is the dimension of our variety. So that would be complex dimension in this case, but then this ends up being real dimension D, like we see in this picture. So it's a support of some polyhedral complex. This is not unique, of course, right? Because we're just saying this is support. So I can also subdivide. Here the polyhedral complex is kind of staring us in the face. But in other situations, it might not be so clear. But you can always put a structure of a polyhedral complex on this. Okay? And of course, if I can subdivide this, and it doesn't change that it's a support, the set of points in the collection of all the polyhedra is the tropical variety. But this polyhedral complex also has a rational structure. So what does it mean that it's rational? It means that every polyhedron, is up to translation a linear space, or parallel to a linear space defined over the integers. Okay, so another way of saying that is for every face of this polyhedral complex, the tangent space of it, so I'll use this as a tangent space, is defined over Z. So we have some full rank lattice inside the tangent space of each face. We're going to use that. Another property is that from this tropicalization, when we have fixed some rational polyhedral complex, this can be equipped with weights. So the weights will be a map WT from the d-dimensional faces of this P. So these are the top dimensional faces of this polyhedral complex, to positive integers. Okay, so here actually in this picture, here are the top dimensional faces, these three edges. Turns out this weight is 1, 1, 1. Okay. The easiest way to get your handle on these weights is to use the definition via initial ideals, I think. I mean, there are various ways of defining what these weights are, but I'll just put in brackets here that the weight of sigma is kind of equal to the number of components of the variety defined by the initial ideal with respect to some generic W in this sigma. So the initial ideal of the ideal of V counted with multiplicities. And this W is some generic point in the relative interior of sigma. Okay, so just that there's some recipe from the variety to get these weights. They don't just come arbitrarily when you have a tropicalization. And in this case, they're all weights 1. And the last part of the structure theorem is that this P with weights, with this weight function, is balanced. So what it means to be balanced is that some condition at each codimension 1 face. So here, our dimension is 1, so codimension 1 is just a single point. And balancing will mean a zero tension condition at this point. So since these are rational, there's a smallest integer tangent vector to each face. Pointing out from the vertex. And if I sum them up with the weights of the face, then I get 0. So this is some zero tension condition. And I want to write this at least ad hoc in all dimensions here. So this is for all tau of codimension 1. We have that the sum of the weights of all of the sigma, so sigma should be a face containing tau. So these are d-dimensional faces. They have weights. And I take the weight of that face times some v sigma. I'm going to say what that is in a second. That this should be equal to 0. Okay, so what this v sigma is, it's not just a single vector, but it's a wedge. It's a d, something in the d-th exterior power of this lattice. Okay, so remember that this has a tangent space, and there's a full ranked lattice, so there's a d ranked lattice in here. Okay, so this is going to be one of the generators of this tangent space. There's only 2. If I take the d-th wedge of t, z of sigma, this is a one-dimensional z module. It has 2 possible generators, this one or minus this one. Okay, but I'm going to take the v sigma, that would induce the same orientation on tau. So here, what that means is that I've taken all the outward vectors. Okay, but there's kind of a unique choice if I want to keep the same orientation on the boundary face tau. Okay, so we're going to see this come up again later. You might have seen the balancing condition phrased differently. This is totally equivalent. Okay, so now that we have this procedure of going from algebra to kind of combinatorics or to polyhedral complexes, we sort of know what images look like. Now the typical thing is to define tropical varieties in Rn using these three properties. So there'll be subsets of Rn that are supports of rational polyhedral complexes of pure dimension d. There'll be a d-dimensional variety. They get a weight function on the top dimensional faces, and they have to be balanced. Okay, so they're weighted, rational polyhedral complexes of pure dimension d satisfying a balancing condition. Okay. I use this to erase? Yeah, okay. And we're going to shortly see that using this definition, even in the most basic of cases, so of linear spaces, that almost none of these tropical varieties arise from algebraic geometry. Okay, so we can look at what happens when we take our V to be a linear space, like we did just now, and tropicalize, and this is how we enter the realm of so-called matroids. Okay. So we're going to let our V now take the form of a linear space. We could ask, what does it mean to be a linear space on the torus, right? Kind of makes no sense, but I'll start with something then in projective space and remove the coordinate hyperplanes. Okay? And there's this early theorem of Sternfels that says that, so let's start with L bar to be a linear space, linear subspace of Pn. Okay, and then we'll take L to be equal to L bar intersect this torus. Okay, then the tropicalization of this L depends only on the matroid. We're going to get to this in a second, but I was sort of warned that maybe many people here have seen matroids before. I know many people have, but we'll get to what we need about these objects known as matroids of L. And this matroid is some combinatorial object. So there can be different linear spaces. Oh, okay, all linear spaces are P, some PD, some projective space linearly embedded. But this L, once we remove the coordinate hyperplanes, once we look at this open thing, the structures can be very different. They could actually have different topologies, different fundamental groups, different structures, but they can have the same matroid. Okay, so this is some forgetting of information, but retaining some combinatorics. But not only that, so this is one point. Second point was that for any matroid, for now whatever that is, can define some subset called trop M, some subset of Euclidean space, which is a tropical variety. Okay, so that means it has these three properties, which I conveniently left on the board. Okay, so it'll be some support of some polyhedral complex. It'll have a weight function. In this case, the weights will be equal to 1 everywhere, like they were in our line example, where we had the tropicalization of the line was the 3 rays, and I put weight 1. And the last thing is that it will be balanced. It will satisfy this balancing condition. Okay, and I said we were interested in recovering the cohomology of our V's, or of our, in this case, our L. And we had in this case that, well, it didn't work when we had something more complicated. But there's another theorem predating this theorem of Sternfels. I think it should be attributed to Orlock, well, has maybe many different attributions. It was conjectured by Arnold and then proved in the braid arrangement case by Brieskorn. And I think maybe the correct attribution is Orlick-Solomon. So this was a theorem about the tropicalization. This is just a theorem about the topology. The theorem about the topology says that the cohomology of our L depends only on the matroid. Okay, and well, what they do is actually even give a recipe of it for it. Let me call the matroid M of L. Oops, not matroids. There's only one. Sorry about that. No, L bar is a single linear space. So this L bar is really like a projective space of dimension D, linearly embedded, okay, so with some sort of n plus 1 linear forms into Pn. Thanks. Any other questions? Right, so they write down a presentation of the cohomology ring. And you can even take integer coefficients. Turns out they're always torsion-free, no matter what L you take. And this is isomorphic to a so-called OS for Orlick-Solomon algebra defined just from this M. Okay, so there's some combinatorial presentation. So both of these things only depend on the matroid, the tropicalization and the cohomology. Okay? You can't go back. If you know the cohomology, you can't recover the L. So as I said before, if you know the matroid, you can't recover the L. There are different linear spaces who have the same matroid, but that are actually, even up to in their topology, are non-isomorphic, non-homeomorphic. They have different fundamental groups. There's some examples of that. Okay, but it's reasonable to ask then, does this, oh sorry, not that, this. Does this know the cohomology? Right, they both only depend on the matroid. Can we recover this? And also, so this Orlick-Solomon algebra, which is the cohomology ring in this case, that you can also define it for any M. Doesn't have to come from an L. Okay, and we can ask, does this trop M know this Orlick-Solomon algebra? Okay. So maybe just another remark before we leave this. So that'll be the goal of the first lecture. Well, to show you how to come up with this algebra, at least, the graded pieces. I won't talk too much about the ring structure for now, from whatever this set is. I should also just maybe mention that here is already an example of where what we get from tropicalizing is very different from what we define as a tropical variety. So in the world of matroids, there's a recent theorem of Nelson, I think from like 2016, that basically 0%, so there's an asymptotic formulation of this, that almost no matroids arise from linear spaces, however this happens. So the world of matroids, which are a notion axiomatized by Whitney and Nakasawa, how to abstract independence in mathematics, they're far more general than the ones that we get from these linear spaces. So already we have many, many, many tropical varieties, if we believe this theorem, which do not come to us from geometry and live only in the world of combinatorics. But once we develop tropical geometry, we can study them with the tools of, we'll see, cohomology, Hodge theory, intersection theory, all kinds of nice things. Okay, so in order to get to recovering the cohomology from the tropicalization, I need to tell you a little bit about what this set looks like, what these sets look like. And the way to do that is to actually describe a fan, put a fan structure on them, and we'll take this, what I like to call the Ardila-Clivens fan. So as I said before, when we tropicalize, we just get a set. And the way that we tropicalize that I set up was to take logarithmic limits. This logarithmic limit set is attributed to Bergman. People often call this fan the Bergman fan. But Bergman never gave us a fan structure. The fan structure that I want to give to you was given by Frederico and Carly Kleibitz. Okay, so just a little bit of what a matroid is. It's just a pair of an E of finite set, so we can think that this is 0 up through n. With some function, rank function, that takes a value on every subset of E. So it goes from the power set of E, all subsets, and here we're allowed to take non-negative natural numbers. And we have to satisfy 3 axioms. But I don't want to write those 3 axioms, okay? Because what I want to do is focus on what properties we're going to want, or what properties we're going to observe or need of whatever these fans are to prove what we need to prove about cohomology and intersection theory and all that. So you're free to go to Wikipedia and look up these 3 axioms. You're also free to think about what would if this was a set of vectors, okay, what would be the properties of this rank function, which is taking to you the dimension of the linear span of a subset. I will tell you, though, that in our example, when we had L bar, then here, we take L bar minus L. This is a union of hyperplanes. One for each coordinate of Pn, because those are be removed, anybody that takes the value 0. Okay, so this is an arrangement of hyperplanes, and the rank function here, so if I take some subset I of these hyperplanes, so we could also take E is the indices, or think of E as a set of hyperplanes. It's just a finite set. This is the codimension in L bar, so in the d-dimensional space of the intersections. All right. So we need an example. All right, so we need to label each of our hyperplanes. Let me label this one 1, 2, 0, 3, and 4. Okay. So then we see the rank, say, of 1, 2, 3. They intersect at a point. A point has codimension 2 in P. This is in P2. All right. If I take the rank of the whole collection, they intersect in the empty set. We define the empty set to have dimension -1, so it has codimension 3. Okay. And then the flats, what we describe as the flats of the matroid. So this is the matroid with this rank function. And a notion for general matroids is that of a flat. So it's going to be a flat if it's somehow closed under adding elements. If every time we add another element, the rank is supposed to jump. If the rank of I is strictly less than the rank of I union J for all J not in I. Okay? So it's just saying that if we have a subspace here from our arrangement, either lines or points, we want to label those. To get a flat, we want to look at everybody who passes through that. So 1, 2 is not closed, but 1, 2, 3 is closed. The other thing that I want to, so we're going to use this. The other thing that I want to use is deletion and contraction. So this is a way of, from a matroid, to come up with two different matroids. You fix an element. Then m minus I is just going to be a matroid on the set E minus I, and we're going to take the restriction of the rank function. The rank function restricted to E minus I. So this is the deletion. And M contracted at I is, again, a matroid on a set of size 1 less. We get rid of I. And we have a new rank function. It's not so important maybe what it is, but I'll show you where it comes up when we need it. The rank will be something like the rank in the original matroid of I union I minus the rank of I. Okay, so it turns out, so this without the index, it's our original rank function. No. So actually, how we should think of this from this geometric picture is, on one hand, okay, depends what you mean by identification. The deletion is you remove the hyperplane, you get a hyperplane arrangement. The contraction is you take that hyperplane, say 3, and you look at the arrangement restricted to 3. So this would be an arrangement on the line. And then, well, we see that 1 and 2 end up becoming the same point. You're allowed to have hyperplanes that are equal. Okay, this means the rank of 1, 2 is equal to 1 instead of 2. I can't hear you.
So in the formula there, what do you mean rank of square I? Or lost I?
So I is a subset.
Okay.
Thank you.
But isn't it always 1?
It may be, if it's always a hyperplane. If you take a hyperplane defined by the linear form that's just constant 0, then it's sort of degenerate, right? Everybody vanishes at 0, or 0 vanishes on everybody, and so the codimension of the degenerate hyperplane is 0. Okay? Thanks. Okay. So how do we get this fan from these notions? This fan will be a collection of cones. Okay, and it's going to live in, well, r to the n, or we could think r to the e, so there'll be one coordinate for each hyperplane. Or n plus 1, sorry, so or r to the n plus 1. But I'm going to quotient this r to the e by the all ones vector. Okay? So it's going to live in this, I mean, this is essentially r to the n. So we're back to where we were tropicalizing to. But this comes from the fact that we have some homogeneous coordinates on Pn. Okay? And as a set of cones, there's going to be one cone for each mathcal f. This mathcal f is going to be a chain of these flats. So if this is our arrangement, we would be supposed to be drawing it in R5 mod all ones. So that's an R4. I'm not going to draw a picture in R4 for you. And it should be, in fact, a 2-dimensional picture. But our flats are really the subspaces on this picture. So the lines and the points that we see, and then we label them according to who passes through those subspaces. Okay, so let me draw instead, if I imagine this big R4, and I have a fan in there, and I intersect it with a sphere. Okay, it's a two-dimensional fan, so I'll get a graph. Okay, if I have a two-dimensional fan in any space and I intersect it with a sphere, I'll get a graph. So that graph is going to look like this. So these are the vertices so far. So each vertex is going to correspond to a ray. I didn't tell you that the dimension of this f is equal to k. Okay? And we can even write down what the generators of this are. They're kind of generated by minus the indicator vectors in my convention. Okay? So it's not so important, but the point is that we get one ray for each flat. So we get one vertex in this graph, which is the intersection. And I get one cone of dimension 2 for each chain of flats, for each inclusion of a point in a line. So if I label this by the flats, then I get so each of these is either labeled by a line or a point. I'm missing some. Sorry. Let me draw the rest after I draw the edges. So I haven't labeled these multiple crossing points. Okay, and then we should see that there's 0 and 3 still intersect in this point. So there's a vertex here. Oh, and a vertex here. And a vertex here. And nothing here, and nothing here, and nothing here. No, nothing here. Sorry. So we could, in fact, bicolor this by making the flats of rank 1 one color, and the flats of rank 2 another color. Okay? So this is the cone, or this is the sigma m intersect with the three-dimensional sphere in S4. We get this kind of graph. Okay. So this is a recipe of the fan, but what's important about it are two things. Okay, so you can look up. One is that there's a self-similarity, or kind of homogeneity-like structure, that if I take any cone in here, then I can look at the star fan. I can kind of look at what's happening locally around that cone. That's the star fan. Then the star of the fan is also a kind of matroid fan. It's a support, has support. A matroid fan for some other matroid. We can describe what that matroid is from the cone sigma f. But what's important is that not only is the fan from a matroid, but at every face, you're also from a matroid. And the second useful thing is that what happens under projections. So if I take a coordinate projection, think of this as being from R to the E mod the all ones, from R to the E minus I mod all ones. And What is the definition of this? I didn't describe it. It's some other matroid that does, I mean, I can, but I'm trying to, we don't need it for now. Is that, well, if I project what happens, this fan, what we get is the fan of M deleted I. Okay, so projection is also a matroid fan. And even as a collection of cones, this deletion matroid fan contains the one of the contractions. So remember, these are both matroids on E minus I. So they live here. And we have this inclusion as sets of cones. So this lives inside. Okay. And what will be important is that eventually we'll see that using these two things, we can go back up to M, to the fan of M. Yeah?
Maybe I missed it, but your fans aren't four-dimensional, or aren't necessarily four-dimensional?
They are, so the maximal cones will be the maximal length of chains. And this is actually, all maximal chains have the same length in a matroid. So they will be pure dimensional.
You have length, is there always a chain of flats with length n? So
not, oh, sorry, it's not complete. This is not complete.
Okay.
And it has dimension equal to the rank function evaluated at E minus 1.
Okay.
Okay? Okay. All right. And in 1 minute, I want to give you the definition or the recipe for from these fans to come up with so-called cohomology ring, this Orlock-Solomon algebra of a matroid, or in the case where we get the matroid from a linear space, the cohomology of the linear space. Okay, so. So these are the so-called multi-tangent or multi-cotangent spaces. So this works for any fan, but we can apply it to sigma m. And what we're going to, so apologize for the same f. It's not the f from the flats. This is a different f. This is going to be a vector space. For each p and for each tau, we can cook up a vector space. Or it's actually, we can do this first over z. So this will be a z module. And what we can do is look at all of the faces sigma that contain tau. Maybe even including tau. And take the pth wedge of the tangent space. And if you like, you can put a z here if you want z modules, or you could also put just the q points or the real points, but we'll take z. What's that?
What's P?
P is this, the pth exterior power. So this lives here. Okay? And then the theorem of, well, and I should say that, so this is the multi-tangent space. And then the cotangent is just to take hom of this to z. So the theorem of Zarkov, which gives us the whole ring structure, so it turns out that if we take the direct sum of all of these for all over all p, fixing tau, then this has a ring structure. Okay, this is a subset of the exterior algebra. This is a quotient of the dual. And we can pick up a ring structure from the exterior algebra that it's a quotient of. And I proved an earlier version of this without using the ring structure. So just that the graded pieces were giving us the cohomology. Is to say that the Orlock-Solomon algebra of M is isomorphic to this whole direct sum of sigma M when we look at the zero vertex. So this is the vertex of the fan, the origin of the fan. And so remember that this means that this is a recipe then for the cohomology ring with integer coefficients when M is the matroid of L. Okay. So the moral of the story is that the only thing that's remembered when we tropicalize is the matroid. Okay? We only needed the matroid to cook up the cohomology. And now we have kind of a tropical recipe, or a combinatorial recipe, from the fan, this tropicalization, for the cohomology ring using these Z modules. This works now not just for sigma M, but this is some recipe for any fan sigma. And notice that I went to all this trouble of doing it not just for the origin of the fan, but I did it also for every cone. So I get a system of vector spaces. Next time, we're going to use this system of vector spaces to define something called tropical cohomology and see what we get for certain objects beyond matroid fans and even tropical varieties. So thanks, I'll stop there.